Okay, so I decided to attack slowly the proof of a simple lemma, which usually is left to the reader. I mean, sometimes it is even not stated openly, and the poor reader has even to understand its existence by himself. This lemma holds for symmetric tensors. So I have a symmetric tensor, and we know, and this I left to you, we know that every symmetric tensor can be represented in this way, where EIs are eigenvectors forming an orthonormal basis. That is a basis of unit orthogonal tensors. Okay. Now, which is the difficulty we have to understand? We have a vector space. Then we have the space of linear maps defined in this vector space into itself. So we have two different objects. We have V and we have lin VV. So the set of linear applications from V into V. This lin includes everything, includes singular linear applications, includes all linear applications, okay? A subset of lin VV is sim VV, okay? The set of linear applications from V into V which are symmetric. Now, what is not trivial? I don't want to say difficult, it is easy, but what is, difficult to understand by oneself is that if V is a vector space, lin VV is another vector space. The set of all linear applications of a vector space into itself is constructed in such a way that it is itself a vector space. We already said this several times talking about matrices, but I want to repeat it once more. So what happens is that you can sum two linear applications and you get another linear application. You can multiply a linear application times a scalar and you get another linear application. Given a linear application, you have minus, of course, now I'm using the wrong order because I should have said before, there is a zero linear application, which is the linear application which added to every other linear application leaves it unchanged. Then you have minus a linear application, and if you are patient enough, you discover that this verifies all axioms of vector spaces. Also sim VV is a vector space, and it is a vector space embedded inside the linear, so it is a subspace, okay? So why I want to tell you this? Because it is easy to prove the following thing, which we already discussed, but it is now very important to understand. If you consider a basis of V, you can construct the tensor product EI, EJ. If you remember, this tensor product is, of course, I have introduced an inner product inside V in order to define quickly this tensor product as we did. One can do things even without Euclidean vector spaces, but in this context it is useless, this abstraction. So this animal, one of these animals, is itself a linear application. Okay? Now, what is wonderful? If EJ is a basis, then this set of linear maps represents a basis of line VV. So every tensor, every linear map in line VVV can be uniquely constructed as a linear combination of these vectors, tensors, vectors. You can consider a tensor as a vector member of the vector space line VV. Okay? So depending on how you are zooming in the structure of your set of objects, you can regard it as a vector or as a tensor. Okay? When you deal with Sim VV, you discover that a basis of Sim VV, and you can try to do the calculations, which are very easy, is constituted by this set. This is trivially the symmetric part of the other animal, up. Of course, 1/2 is not essential in this context. Okay, and using this set of tensors, you can, via linear combinations, you can produce every symmetric tensor. Okay? We stop for a moment talking about the structure of line VV, and we go back to our lemma. If S is a symmetric tensor, we have proven it has an orthonormal basis of eigenvectors, and this representation formula is trivial, because you apply S to EH, this is equal to this inner product by definition, which is what you need to use by definition, because A tensor B applied to C is the inner product of the two closed vectors on the right times the first vector. Okay, so you get that this, as this is an orthonormal set of vectors, this is equal to okay. Now, you could be willing one time to do all calculations without the index summation Einstein-Levy-Civita-Einstein convention. Look, that expression is a nightmare if you write it explicitly. So the reason for which you need to learn, by the way, now I will write for you the formula in 3 dimensions, but this is valid for any n. And I recall you that n 1 million is a conceivable n. So here I can write L1 E1 plus L2 E2 plus L lambda 3 E3, which is the so the complete expression we have in 3 dimensions is this one. I am already tired, okay? This is the complete form, the explicit, how to say, unfolded version of this formula. Then you can do dot E1 or dot E2 or dot E3. So you have to write 3 of these formulas. Okay, but I'm lazy, I will not do it. Then you write equal. Then you discover that E1 dot E1 is 1, and you get lambda 1 E1, plus E2 dot E1 0, E3 dot E1 0, and you are left with a particular form when h equal 1 of this formula. So instead of writing 3 of these formulas with the clever notation by Levi-Civita, you are able to write only 1 line including all these formulas. So this is a powerful tool. You cannot give up. You cannot decide I don't want to use it, because otherwise the set of achievable calculations for you becomes much smaller. So this is the really important message which I want to send to you. Of course, this calculation, when n is large, is not even conceivable by hand, and this formula is very powerful because it allows you to get a result for any n. So it is clear that all these things may be very difficult to understand, but they are difficult to understand because they are powerful. And you never get something for free. Okay? Now, I need to do 2 different calculations. First, I need to assume that the 3 eigenvalues are different, one from the other 2. So these 3 inequalities hold. Then we will try to do some calculations to prove that identity S and S square form an independent set in the vector space Lin VV. Now I understand it is somehow difficult to understand. S is a linear map, but it is also an element of a vector space. S square also. Okay, so what I'm telling you that these 3 linear applications regarded as vectors in Lin VV, they form a set of independent vectors. But what is important is that span of 1S square, that is the set of all linear combinations of 1S and S square, this span is the same as the span of EI tensor EI, where EIs are the eigenvectors of S. So either you consider all linear combinations of these linear maps, or you consider all linear combinations of these tensors, you get the same vector space inside Lin VV. Okay? So, who among you is familiar with the representation theorem for isotropic functions of tensor variable, symmetric tensor variable, already starts to see where we are going. Okay? But in details we will see everything. Assume instead that lambda 1 is equal to lambda 2 and these two coinciding eigen values are different from lambda 3. Then, if E is one of the eigen, we will see in detail, one of the eigenvectors, span of identity and S is equal to the span of identity E tensor E. So what we have said before applies, but in a particular instance. I mean, instead of considering 1s squared, now we have 1s, and the span of 1s is equal to the span of 1 and E tensor E. Okay? So what we do now, we try to prove 1 and then we prove 2. Okay? You will discover that these are very easy calculations. You simply need to be very, very patient. I hope we have space enough on the blackboard. So in order to do everything without losing the point, what it means that these three form a linear independent set of vectors given alpha, beta and gamma, assuming that this is equal to the 0 vector, which is the map which maps every vector into the 0 vector, okay? We must discover that this implies alpha equal beta equal gamma equal 0. This is the definition of linear independence. Okay? So here we are living at the level of lin VV as a vector space. Okay? Now we zoom in this vector space and we discover that this vector space is made of linear maps. Okay? So what we do? We consider an eigenvector of S and we apply this linear map to this eigenvector. Okay, now it is trivial that S squared applied to EJ is equal to lambda squared J, because you apply S 2 times. First time you get lambda EJ, second times you get another lambda EJ. Okay? So this is trivial. So this implies this is equal to 0. So this implies that alpha plus beta lambda J plus gamma lambda J squared EJ equal 0. I'm simply calculating these three linear maps on the eigenvector. Okay? Now, every eigenvector is different from 0 by definition, so we are left with this. Okay. Now, we go back to polynomial algebra of polynomials. Okay? We have three numbers which verify three distinct numbers, okay, which verify the same quadratic equation, polynomial equation. This is possible only if and only if alpha, beta, and gamma are all 0. The result is well known. When you have a polynomial equation of second order, you cannot have more than 2 roots. If you have 3 distinct roots, then the polynomial is the trivial one. Okay? So, as a conclusion, we can get that. So, I hope that you are learning that these apparently esoteric results are all constructed with very simple, very simple methods. Okay? Now, in order to understand that span of this and span of that are the same, you need to calculate S square. Okay, you can do the calculations and you discover that S square is equal to this expression by brute force. You write S one time, you write S another time, you develop all calculations, you use the properties of Kronecker delta, which comes out several times, and you get this result. But this is a useless, brutal calculation, because we have already understood that an eigenvector of S is also an eigenvector of S square with the corresponding eigenvalue given by the square of the previous eigenvalue. So we know that S square is symmetric because it is the square of a symmetric tensor. So we know it can be represented as such a formula where E are suitable eigenvectors, and here you consider the corresponding eigenvalues. We know that you have a basis of eigenvectors of S square. You know that Ej is an eigenvector of S square, so you already have the basis of eigenvectors. And the corresponding eigenvalues are lambda I square. So it is trivial, without calculations, to see that S square is given in this way. By the way, I want to open a small, completely useless bracket now, I mean, parenthesis if you want. What it means, logarithm of a symmetric linear map, or what it means E to the linear application A. We have a very powerful spectral property. We could, of course, you have to be very careful when you can do this or not, but you can write this way. I mean, this is a very naive observation. A true mathematician would claim I'm crazy, but you can make all this rigorous. Of course, logarithms are possible only for positive real numbers. So logarithm of a is possible only if a has positive eigenvalues. So you are slowly introducing the calculus of matrices. So you can introduce elementary functions whose independent variable is a matrix. Okay, this was conceived by Dirac for founding quantum mechanics, and then is used everywhere in every part of mathematical physics. Okay, so I close quickly this parenthesis and we go ahead. Why? Because now it is clear that S square is in the span of EI tensor EI. S is in the span of EI tensor EI. The identity is in the span of EI tensor EI, trivially. And vice versa. But we don't need to do calculations, because we have studied that in a vector space, when you have an independent basis, every other set of linear independent vectors having the same cardinality of the previous one is itself a basis. So if you have a three-dimensional space and you find three vectors in that three-dimensional space which form a set of linear independent vectors, you are sure that these three form a basis. So we don't need to do the opposite calculation. So we do not need to prove that E1 tensor E1 can be written in a linear combination in terms of 1, S, and S squared, because the general theorem valid for vector spaces is assuring us this. So in a sense, I want also to prove you via this example that mathematicians are lazy. Instead of doing complex calculations, they prefer to prove something using a rigorous abstract reasoning. So, in a sense, these complex theorems are an extension of our calculation power. Okay? Okay, let's go ahead. So, assume that you have two distinct eigenvalues. So S can be written in this way. Lambda 1 E1 tensor E1 plus E2 tensor E2 plus E3 tensor E3. I hope that you easily see that this is equal to the identity. Okay. Plus lambda 2 minus lambda 1 E2 tensor E2. What I have done, I have, okay, maybe it is worth to write the first formula. Lambda 1 E1 tensor E1 plus lambda 2 E2 tensor E2 plus lambda 3 E3 tensor E3. Okay? And lambda 1 and okay. So we have two eigenvectors, eigenvalues which are the same, and the third which is different. Okay. So maybe I'm using the wrong indices. So let us check. This is equal to that. Then this one, so yeah, it's right. I was jumping the calculation here, so I want to check that I'm not misleading you. Okay, so I am simply adding and subtracting the same thing. So this is the spectral representation of S when lambda 1 and lambda 3 are equal. And I'm rewriting S in this way. Now, do you recognize that this is equal to the identity? If not, I do the calculations. So if I have some EI, tensor EI, applied to V, this is equal to V sum VI EI, which is equal to V. Because if you remember, the inner product of a vector with the generic component of an orthonormal basis is equal to the component of that vector in that basis. Okay? So this is something which they are teaching us in high school. So the identity can be represented in this way. Okay? So span of this equal span of that is trivial. I have written. Okay? So what we have left, what we have now to calculate, and maybe I can leave it to you because these calculations are written on page 269 of the book. Okay, what is very trivial but needs some calculations is to prove that this is actually an independent set. The trick is always the same. You consider a linear combination alpha identity plus beta S, you calculate it on EJ, you assume that this is equal to 0, okay, and you get this time a linear system homogeneous in which alpha and beta are the unknown and the determinant is different from 0. So with few calculations I can skip. You discover that you have a matrix A which applied to the vector alpha beta is equal to 0, and this matrix A is this one. Now use Rouchet-Capelli theorem. An homogeneous system whose matrix of coefficients has a determinant different from 0 has one and only one solution. And as it is homogeneous, you can only have alpha equals 0, beta equals 0. The determinant of this animal is lambda 2 minus lambda 1, and by hypothesis, this, okay, of course I'm mixing.
And I think the better thing you can do is just change that.
Yeah.
So lambda 1 equal lambda 3 and so
Okay, with this trick, everything works. Okay? So, yeah, I think that what I've done, I have changed my mind about which had to be equal, which eigenvalue had to be equal to which other one. Okay, so we have proven that with linear combinations of 1 and E tensor E, you get the same set of linear applications which you get using linear combinations on 1S. And we have done the same with EI tensor EI and 1S and S square. Okay? So let me check. We needed a lot of time. Okay? But now we have a powerful tool which we can try to use. At the end, I tried to find a quicker demonstration than the standard one. And I found it. But it is so quick because it uses many other properties. Okay. And to prove the other properties was longer. So we can say this, that there is always a balance of pain. Okay, for proving something, you need a minimum amount of pain. Of course, if you are good, you can increase this pain at the level which you like. Of course, it is like dissipation. You can increase the number of pain, but there is a minimum threshold under which it is not possible to go. I believe that this version of the theorem, which we need to prove, this version is the one which is minimal in the dissipation of efforts. By the way, it is also very, very useful from the intellectual point of view. I mean, you learn a lot of things which are not difficult and which are very, very useful. So, imagine to have a map Y of S which is isotropic. So you have a map defined in the set of symmetric tensors in the set of symmetric tensors. What is powerful in the modern mathematics is that set theoretic concepts are dominating everywhere. So you have the set of symmetric applications. And then you have a map which takes any element in symmetric VV and it maps it onto another. So if you don't use the right symbols and you use the wrong words, you risk to be lost. Because if you call S map, you have a map Y mapping a map S into another map Y of S. So you become crazy. Okay? So the importance of introducing suitable names and suitable sets in this context is essential. You have to consider mathematics as a structure built on another structure, which is built on another structure, and so on. And you have always to choose the right level where you locate yourself because you are interested in a particular property in a given moment. So now you have a map which takes sim into sim. Okay, this map being verifying this property, isotropy. Okay? We motivated this property from a physical point of view, and I tried, but we will go back again to this point, I tried to make you clear that these particular functions are very important in mechanics. Okay? Please do not give any particular meaning to S and any particular meaning to Y of S. This is an abstract theorem. You have a map from sim to sim which verifies this condition, where Q belongs to orth. So it's an orthogonal map in V. Okay? Now, I don't know if what is written in books, now I'm changing a little bit my mind, is true. This theorem is sometimes believed to be proven, to have been proven by Rivlin and Ericsson. But I suspect that at least a conjecture about this theorem is already present in Lamé. Okay, but so it is not clear, but this is another story. In this moment, we need to prove it. Okay? Now, what is very powerful and elegant is that Y of S is equal to, simply because of this assumption. So, this assumption implies that Y of S is equal to a scalar V0, we will tell which are the independent variables of V0, identity, plus V1 times V, plus V2 times V square, and V0, V1 and V2 are functions of the invariance of, sorry, here is S square. Here are the invariants of S. So the first, the second, and the third invariant. So, in the enormous set of possible maps defined in sim, having values in sim, to assume isotropy means that you have this very particular form. Okay? We will discover, the last discourse will end with a discovery. We will discover that in linearizing this map, so once you assume that this map is linear, so when you can neglect in a Taylor expansion all higher orders, all squares in this formula, then it reduces to a map in which only two coefficients can be chosen. These two coefficients will become Lamé coefficients in linear elastic isotropic theory, and they will become the two Stokes-Navier coefficients in linear dissipative Navier-Stokes fluids. But this theorem allows you to remain non-linear in general. I want to say that when you have only isotropy. The most general isotropic map is constructed once you have chosen 3 scalar isotropic functions. So the constitutive theory of isotropic tensor, symmetric tensor valued functions of a symmetric variable is completely known if you know these 3 scalar quantities, which is crucial in many applications. Okay, now it is very easy, I hope, to check that y of s is itself isotropic. So when we need to prove a necessary and sufficient condition, so the 2 implications. I didn't tell you the implication before, that this implies that, because this implication we have already seen and it is trivial, but let us check. The invariants are invariant. So when you consider Q as Q transposed, these invariants are the same. So V0, V1 and V2 are left unchanged when you replace S with Q as Q transposed. So to prove that this function is isotropic requires simply to prove that Q identity Q transposed equal identity, which is trivial. Q S Q transposed is equal to Q S Q transposed, which is trivial. Okay? And then Q S Q transposed Q S Q transposed is equal to Q S squared Q transposed, which is also trivial. So if you apply Q and Q transposed on the left side, you apply here, linearity allows you to distribute this, and using these 3 equalities, isotropy is trivial. Okay? So what is really painful to prove is the implication which I had written before. Okay? But now we have all tools for doing this. I mean, you will see that with the theorems which we have proven already, this representation is very easy. Now I need to recall something. We have proven in the previous lecture that an eigenvector of S is an eigenvector of Y of S once you have accepted that Y of S is isotropic. So, an application defined in Sim, having values in Sim, is mapping a symmetric tensor in another symmetric tensor, and under this transformation the set of eigenvectors is preserved. This is the crucial property, which we have proven with simple calculations in the previous lecture. Okay? So now what we have to do? Assume case 1. Assume that the symmetric tensor V has 3 coincident eigenvalues. So V is equal to alpha identity. This is a spherical tensor. The reason for which at the end I decided to present to you the standard version of this theorem is that at the end of this, if you have understood carefully this theorem, you become familiar with spherical tensors, eigenvalues, eigenvectors, representation theorems in the set of symmetric tensors, and these things which are all very useful by themselves. So you have that V is a spherical tensor, and which is very elegant, so we don't need to do calculations. The set of all eigenvectors of V is the whole three-dimensional space. But being eigenvector is inherited by Y of S. So Y of S
so this is S rather than V?
I don't know why I'm confusing all the time. Y of V is a symmetric tensor for which every vector is an eigenvector. Okay? So the eigenspace of Y of V is the same as V. So because of the previous theorem, we can say that you have a V0 which itself can be a function of the invariance of V times the identity. Okay? So, the structural property of isotropic functions of symmetric variables, symmetric tensorial variable, which tells you that every eigenvector is an eigenvector of the image, together with a theorem about symmetric tensors. This is the form of the symmetric tensors having the whole space as an eigenvectors. Okay, spherical symmetric tensors are the only tensors having as a space of eigenvectors the whole space. Okay? So, if V is spherical, Y of V is spherical, so this formula holds. Okay? So this is the reason for which I don't like so much this proof. You have to be patient and you have to treat all cases separately. There are difficulties if you want to prove this in n dimensions. You understand? Okay? So if one day you need to prove something about isotropic functions from symmetric to symmetric tensors in n-dimensional space, this proof is not good. Because you cannot spend all your life assuming what happens if k are equal and n minus k are different. I mean, the characterization becomes more complicated. Okay, so next step. Assume that V is equal to alpha identity, as we have seen before, plus beta minus alpha E tensor E, which is the case of two distinct eigenvalues. Okay. Now, the proof which we have already given implies that y of V must have the same eigenspaces. Okay, so as we have done before, we can represent y of V as V0 identity plus V1 V. Now, you may believe that I'm jumping. You could say, why you are not writing V0, V1 minus V0 E tensor E? The reason is that we have already proven that any linear combination of this form is equivalent to any linear combination in this form. Okay? Span of identity V is equal to span identity E tensor E, if E is an eigenvector of your linear map. Okay? So I'm doing things too quickly. So y of V is of this form, which is a particular case of this form. However, I'm keeping aside the problem of the dependence of V0 and V1 on the invariance of V. We will treat this case, this problem at the end. Okay? Then we have last step, but we have understood now that the previous lemma was prepared explicitly for what we are doing now. If you have three distinct eigenvalues, you have alpha E1 tensor E1 plus beta E2 tensor E2 plus gamma E3 tensor E3. The last part of the previous lemma tells us that E1 is an eigenvector of V. E2 is an eigenvector of V, and E3 is an eigenvector of V. So y of V has exactly E1, E2, and E3 as eigenvectors. So even if logically this I should have written before, we can say that you have lambda 1 E1 tensor E1 plus lambda 2 plus lambda 3. Okay? So y of V is a linear combination of E1 tensor E1, E2 tensor E2, E3 tensor E3. However, we have proven in the previous lemma that 1 V and V square belong to the same span as E1 tensor E1, E2 tensor E2, E3 tensor E3. So we can rewrite the formula in this way. So again, we have proven this structure. What we have left? the dependence of V0, V1, and V2 on the independent variable. So for completing the proof, we need to prove that V0, V1, and V2 are isotropic. Okay? Okay, now I ask you to jump some calculations, but they are trivial. I write this representation formula here. What I get? It is easy. I get V0S minus V0 QS Q squared times the identity. Okay? If I'm writing QYS Q transposed, I get V0S identity. If I consider Y of QS Q transposed, I get V0 QS Q transposed identity. Okay? So this is, now you have understood what we are doing. V1S minus V1 QS Q transposed S, okay, plus V2 S minus V2 QS Q transposed S squared equal 0. So it is clear what we are doing. We are writing, we discovered that an isotropic function y of s is of this form. However, we have not yet discovered how V0, V1, and V2 depend on S. We simply know that they are scalars. So we have proven an intermediate step. We have proven that if y is isotropic, then it is of this form where V0, V1, and V2 are scalars. Okay? Now, next step. We consider this structure which we have already got, and we write another time this condition. So we can write this minus this equal 0. You replace and you get this identity. Okay? But which linear combination of 1 s and s squared is giving to you 0? We have painfully proven that the only linear combination of these three tensors producing the 0 tensor is the linear combination with vanishing coefficients. So we prove that V0, V1, and V2 are isotropic. So in order to complete, if you want to persuade yourself, you need to write this equation here, and you get this. Okay. So now we have the whole of course, for doing this identity, you have to use another time that Q identity, Q transpose is the identity, Q V square, Q transpose. I mean, what is typical of books written by mathematicians. I don't want to exploit the absence of the poor Sandro Bishara, who cannot defend himself anymore. But, you know, mathematicians are very often writing very trivial things, and they are omitting very complicated things. Okay. But here, you need simply to write this formula explicitly on a sheet of paper, and you get the result. Okay, so I think we can stop here, but I want to repeat you what we have got. We have proven that a map which associates to every symmetric tensor another symmetric tensor, which is isotropic, needs to have this form: V0 identity, V1s plus V2s squared, where the three scalar function V0, V1 and V2 are functions of the invariance of S. So now we know how to write the generic constitutive equation, which is isotropic. What I want to do in the last lecture of this course is the following, which is very important for you. I want to prove that an important part of the constitutive theory for viscous fluids and an important part of the constitutive theory for isotropic, linear, elastic or elastic solids is a consequence of this representation theorem. You are old enough and you want to become a researcher. So you have to learn that a theorem is not a theorem about the mechanics of fluids. A theorem is a logical property which is true because of a set of definitions. And it is absolutely stupid to teach with some reasonings in a class of mechanics of fluids how looks like the constitutive equation for a viscous fluid, and to repeat, possibly with different symbols, in order to hide carefully this, in the class of solid mechanics, the same representation theorem but applied to elastic solids. This is so stupid because in this way we are wasting your intelligence and your time. The big problem is that because of Napoleon's decision of dividing the professorships in groups, and because of the crazy choice of deciding that somebody is professor of fluid dynamics, somebody else is professor of solid dynamics, solid mechanics, fluid mechanics, at the end, completely separate cultural ambience were developed, which are not talking one with the other. So, we are teaching stress tensor with different symbols in different courses in a completely different way in order to make confused in the head of students that we are talking about the same object. And when you talk about Lamé moduli, you carefully avoid to tell that the representation theorem is the same, which has to be used for introducing Navier-Stokes dissipation moduli. So this is a small part of a much more complicated story, but I want to tell you that you have to open your eyes and you have to understand what is peculiar of a fluid and what instead is a general property which must be framed in a more general setting. Okay? So I exploited the need of proving this for giving a very, how to say, an higher order message. Okay? Okay, thanks.
Can I ask a question?
Yeah.
What will change in this theorem if you change the group of invariants? I mean, we have rotations, you can have some sort of orthogonal or something.
Okay, you are a bad boy. Okay. Okay, so it's his fault. Okay. So he obliged me to tell you which are the fundamental ingredients of this theorem. You know, mathematics is like this. I like very much mathematics because you can study the same subject at different levels. You can go very low, use plus, minus, and you can go up and up and up. So the question is, how can I generalize this? Which are the ingredients? Okay. So I hope that you know about groups something. Okay. We don't need to go in such a detail. Let us say, talk about Lin LVV. Okay? So we have a map, actually, look, it is possible to generalize what we have done with some difficulties in Lin, but we preferred to stay in Sim for several reasons. First, because the applications we have in mind are dealing with symmetric tensor. Second, because a symmetric tensor can be represented in that nice way using eigenvectors and eigenvalues. So for using a very complex expression, we used spectral properties of symmetric tensor for proving our theorem. So, first ingredient. What is a symmetric tensor? In order to be able to define a symmetric tensor, you need an inner product. So you need to say what is W inner product V in the bottom vector space. Why? Because you need to introduce the transposed. The transposed is fundamentally a property related to inner products. Okay? If you remember, AV inner product W equal to V inner product A transposed W. This is the definition of transpose. So if you don't have an inner product, you are lost. You cannot even start. But what you are doing, actually, you have a function and you want it to be invariant under some transformation of the independent variable. Okay? Which transformation we have introduced? The rigid rotations. So we wanted to study what happens if you compose S with Q transposed Q, so if you change the observer in the mechanical application you have in mind. But you know, this is an invariance property for every element in a given subset of lim. Okay? So as I told you, you are familiar with level sets of functions. What you are telling that the YQS Q transposed is close to YS once you transform the image somehow. So this is a property of level sets for Y of S. But more important, you need to define an orthogonal the set of orthogonal linear maps. So again, you need an inner product. Okay. So this theorem, for sure, can be proven in a more general setting when you have pseudo-linear transformations. Pseudo inner products. So in general relativity also is needed to introduce isotropic functions, but Q are not orthogonal in the sense of classical mechanics, but in the sense of Minkowski transformation. So for sure you need this transformation. But more generally, there are all theories of invariant scalar quantities under groups, Lie groups applying on the linear operators you have in your hands. So this animal can be generalized. However, you need an inner product structure. I am not aware of any such theorem in a more general setting. I could be wrong, but I mean I've not seen any generalization. Okay, so actually this stuff can be generalized a lot, but for our applications, three-dimensional ones, this is enough. General relativity needs this representation, and it is easy. I mean, it's not so difficult to generalize from here. You need inner product, so some of these passages, and you need to be in 4 dimensions, so it is more delicate.
But for instance, when you have an isotropic material with certain symmetry, maybe, I don't know.
A group of symmetry.
Yeah. So for instance, you have a crystal, and a perfect crystal, and so on. Then you can do something similar to that.
No, there are delicate representation theorems based on Schur lemma and on complex tools of Lie groups theory, which allows you to give the complete classification of linear or in a given class of non-linear materials, which are the functions which are orthotropic, for instance. I mean, not only there is a total classification. So, given elasticity, you have linear elasticity, you have all classes of symmetry which are classified totally. So these are theorems which started to be proven in the 40s and still are proven. For instance, I am communicating recently a paper in which the most general orthotropic second gradient elastic material is represented. So these theorems allows you to know which is the most general orthotropic second gradient material. So you have 4th order tensor, 6th order tensors which are invariant under a given class of a given group of symmetries. So it is painful, but I mean, it is done. It is done. As we are talking, then I leave you go. Of course, you can have a delirium of omnipotence, and you can decide that you want to represent isotropic scalar functions, let us start off, as a vector V, another tensor of third order C, and so on. And there is a theorem which allows you to construct all invariants, and the scalar quantity will depend on all the invariants built with the independent variables. So the theorem is not so easy to generalize when you have more than one variable, but still you have the tools. Isotropy is completely known in any case. Ok? Va bene.